All right, we'll start out with any last minute questions from chapter 6 or 7.
If you're trying to figure out what impulse is needed to stop something from moving, do you just take the negative of the momentum?
Right, because once you stop it, the momentum is 0. So, yes.
And then in chapter 6, number 37, the second part.
One's driving north, one's driving east.
Yeah.
So this is 37. I guess 37B. All right, so you have one traveling north and one traveling east, assuming classic east, north. And 1,000 kilograms. $20 meters per second. 20 meters per second. Because it's a two-dimensional problem, we can't get away with just plus and minus. We have to deal with I hat, j hat. So the total momentum beforehand, well, you take each one separately. And somewhere there's a marker that writes dark. Since it's two-dimensional, let's set up our coordinate system, I hat, j hat. All right, so what is the momentum of this one? Yes. Units?
Kilograms times meters per second.
Yes. Kilogram meters per second, I hat, because it's going that way. Or you could write out east, or there's several ways of doing it. What's the momentum of this one? Okay. So 20,000 kilogram meters per second. Let's put the commas in there.
Isn't that also newtons?
No, Newton is a kilogram meter per second squared.
Okay.
So this is the same as a Newton second. So you could also do that as a unit, or make up your own and just define it somewhere. J hat or north to this one if you want to write out the shorthand or write out the words. So this is the momentum before the collision. So after they collide, what's the total momentum?
Two square plus 20,000.
Ah, okay. I'm going to take an intermediate step before that. There's a middle step. It's the same thing. You went ahead and did the addition. So the total momentum before equals the total afterwards. So this is what it is afterwards. And it depends on how does he word the wording. At what speed does the wreckage move? So in essence, we have these two vectors here. We have this 20,000 going this way and 20,000 going this way. So the sum, because we're adding them, that's the sum, which is 20,000 times the square root of 2, as Naveen said, or 282, whatever, 20, Pythagorean theorem. That's 1.41, so it's something like that. But that's the momentum. The question's asking about the speed. So it's not asking about the vector piece of it, or the direction piece of it, at least not in that set. But that's going to be equal to the mass times the velocity. Or, since we're talking about just in one direction, the mass times the speed, so it's 28,200 is equal to mv, and the mass, well, what is the mass of the wreckage?
40,000.
Not 4,000. How'd you get?
40,000.
No. Mass.
Oh,
Uh,
2,000.
Yeah, 2,000. Because we have 1,000 kilograms here, 1,000 kilograms here, and they become 1. It's the romance story of the ages. So we have 28,200 is equal to 2,000 times v. That's the math problem. And so the speed of it becomes
14.
meters per second. Now the direction is asking, well, that's north, that's east, and it's traveling that way. So it's going northeast. Or 45-degree angle. Although I think northeast is what he has written in the back. It's probably a little bit more accurate, given the context.
So you're multiplying, I'm sorry, to get to 28,200, you multiply 20,000 times the square root of 2?
Yeah, so if I've got a triangle where this is length A and that's length A, and that's C, I know that A squared, right angle, A squared plus A squared is equal to C squared.
Okay.
In Pythagorean theorem, it's A squared plus B squared equals C squared, but these are the same.
Okay.
So that's 2A squared is equal to C squared. And if you take the square root of both sides, that's an A. C is equal to the square root of 2 times A. So that's where the square root of 2 comes from.
Oh, okay.
If you just did Pythagorean theorem, you're good. The shortcut is, if those are the same, it's just that times square root of 2.
Because I got a totally different number when I did that. I got like 28,200 and something.
Oh, yeah, because square root of 2 keeps going, there would be some other numbers there.
Okay. I just wanted to, okay. All right. Thank you.
Okay, that's what was
That's what
confusing me, because like, I didn't know that they rounded down, so I had gotten like 28,284 instead of just the even 200 stuff.
That's what I couldn't figure out either. I was like,
Oh,
how
okay.
did you get the, I was trying to figure out how I got the 28, how you got the 2,200, because I got a totally different number.
He was trying to make it easier on you.
Okay.
Apparently that didn't work this time.
It just confused me, that's all.
In chapter 7, number 54.
All right, any other questions on this before we do chapter 7, number 64? Oh, you said 6-4?
54.
54. 54. There we go. Yeah. What I find odd is the number 54 there, actually I think should be in chapter 2 instead of chapter 7. But there it is. All right, so ranking the readings. So basically what the scale is reading is the tension in the rope. So whatever force the kid is pulling, with which the kid is pulling, will be the tension in the rope. That will be the measure on this. We are assuming that the weight is being sort of held still off the ground. In other words, it's not accelerating. We are assuming that this mass is in equilibrium. So acceleration is 0. Therefore, the total force is 0. So in this case, we have, it's the same container each time, right? Yeah. We are also assuming that the box is the same in each case. It has the exact same weight. So if I look at the force diagram here, it has weight acting down, we have tension acting up. So he has to pull, since these balance out, since the total force is 0, these two forces must equal each other in magnitude. And so the tension is equal to the weight. That's for A. All right. Any questions about just A before we talk about B and C? All right, so B, we've got the more complex system here. It's somehow attached there. Now, I've drawn it at slightly more of an angle than the way Hewitt drew it. We are assuming that he is pulling straight, that the kid is pulling straight down on the rope. So that really should be straight down. Recognize that here we're lifting the mass. Here we're lifting the mass and pulley. So the mass and pulley is basically one object. Now I'm going to assume that the mass and pulley here weighs the exact same as just the mass. A nice ideal pulley. So if we look at the forces acting on this, on our mass pulley system, well, I have tension acting up on two sides. And because tension's acting up on two sides, the 2 times the tension is equal to the weight, or the tension is just half the weight. The advantage of a pulley. Questions about part B, or choice B. And then in C, it's attached to something up here, and this one is being pulled up. This is the same situation as in B. This is C. It's the same situation there, in the fact that I've got my pulley mass system here, and it's being pulled up on two sides. And then I have this weight acting down. So B and C are the same amount of tension. So rank the scale readings from highest to lowest. This would be the largest scale reading, and then those would be tied. So that would be A is greater than B equals C. Now, one of the reasons why this is in this chapter, and he doesn't actually exploit that, as I don't think there's another problem related to it. If you want to lift the mass 1 meter, so you want this thing to move up 1 meter, then he has to pull down 1 meter here. In essence, he's putting work into it of whatever the tension is times 1 meter is the amount of work he's putting into it. And so this increases its potential energy by, let's use some numbers here. I'm going to make that 2 meters this time. Let's make the weight of this equal to 10 newtons. So if he pulls on this rope 2 meters, he is going to do 20 joules of work, force times distance, or displacement. And the potential energy of the mass is going to increase 20 joules. Now over here, he wants to add 20 joules of energy into it, so he's going to take this mass, and again, we'll assume it's 10 newtons. He wants this to raise he wants to raise it 20 joules, so it's going to raise 2 meters. However, on this side, since he's only doing half the work, or applying half the force, So he's applying 5 newtons of force. He has to pull this thing 4 meters. So 5 newtons times 4 meters is 20 joules. So by cutting the amount of tension in half, he does have to do it longer. And that's one of the reasons why this type of problem shows up in the energy chapters. It's just that it seems odd the way he presents it. But I was not consulted, so there it is. Other questions about this problem?
So he has to pull it 4 meters to raise it 2 meters?
Yes, because he's doing half as much effort, so he has to do it for twice the distance. All right, other questions from chapter 6 or 7?
What's the units for power?
Watt. Since power is the amount of energy it takes per time or the work per time, depending upon context, these have units of joules. This is a unit of seconds, and a joule per second is a watt. So these two W's here are not the same. This one is work, this one is watts. Another one of those lovely things in physics where they ran out of letters. Not the worst case of unit and variable looking the same, but it's up there. All right, other questions from 6 or 7? All right, let's get this quiz out of the way. All right, let's pick up where I think we left off. Seems like we got this far for the kinetic energy. And again, I'm going through this just to show that it comes from somewhere, not necessarily for you to just throw it back up at some point. So what's a radian?
It's like a way to measure that unit.
Okay, so it's an angle unit of measure.
Half of the diameter.
No. Why are there 360 degrees in a circle?
Because it goes all the way around.
Okay, but why 360? Why not 400? Was that?
I said we can, but it would translate to something else as well.
True. And the 400, there's something known as a gradient with a G up front, which breaks it into, there are 400 gradients in a circle. It used to be on calculators. I don't think they do use it anymore. Okay, so we actually can blame the 360 degrees on the Babylonians. So they realized 60 was a special number. And actually 60 is a pretty amazing number because it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. It's divisible by a whole bunch of numbers. And they associated 60 with having some sort of, my understanding is they connected it with the religion, and then they connected it with the equilateral triangle. Because we have a perfect shape here, all the angles are the same, all of the sides are the same length, and so they associated 60 with each of those. We now call them 60 degrees. And they noticed that if you take 6 of these triangles, you can put them together and it comes out complete. It sort of fits very nicely with each other. And if that's 60, and 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 that's 60, well, it's 360 all the way around. That's where it comes from. I believe it was in the 19th century when the French mathematicians, primarily the French mathematicians, said we want to eliminate as much artificial, man-made structures in math as possible. It's possible it predates this, but I'm going to associate it with them anyway. And since degrees is man-made and artificial, they wanted something that was natural to circles. And they realized that if you take the radius of a circle, so imagine I've got a perfectly round circle, I take this length of the radius and I wrap that radius around the edge so that this arc length here is equal to that. They noticed that that angle is the same no matter what circle you're using. And that's what they said was 1 radian. They felt it was a natural unit for an angle. And then they figured out, well, how many degrees how many radians are there in an entire circle? Well, since you have an angle of 1 radian for every radius that you could wrap around the side, well, how many radiuses can you fit around the entire circle? In other words, what's the circumference of a circle? Say it again. Circumference, the distance.
Oh.
And a little bit. We can get it more precise than that. What's the formula for an area of a circle? Okay. Circumference is the other one. What's the other formula? That's the one. Circumference is 2 pi times the radius, which means that I should be able to fit the radius around the edge of a circle 2 pi times. There's 2 pi radiuses around the circle. So that's why a circle, 360 degrees, is the same as 2 pi radians. But by then, 360 degrees is so ingrained that it's not going to go away anytime soon. However, there are times in which it is convenient to be using radians. Now, what they realized is however many radiuses I have, so if I have, let's say that's a half of a radius there, so if I have 1.5 radiuses, 1.5 radii, I have 1.5 radians. So my angle relates very much to how many radiuses I can wrap around the side here. And it comes out that the number of radians times the radius is just going to be equal to the arc length. So this is arc length with an extra letter. Arc length is equal to radius times the angle in radians.
Is that supposed to be like an S?
Yes, it's supposed to be an S. Going back to the Latin stadia, which was a unit of measure for length. Now, so if I have arc length is equal to r times theta here, if I'm looking at an angle, it's really, I'm going to throw a change in there. So the change in the arc length, or actually technically it's the distance, is equal to r times whatever angle there is. Sort of a hand wave going from here to here. This is the way the math people express it. This really should be the way the physics people express it. And then I'm going to divide by time. So if you imagine I have something actually moving around the edge here, so I've got a bug or a circular track and a car's going around it. It takes a certain amount of time to get from here to here. It takes the same amount of time to go through that angle. So what I have here is I have distance divided by time, which is just speed, which is equal to the radius times, well, I have change in angle over change in time, which is angular speed. Angular speed, and the symbol here is an omega. It is not a W. We use W for too many other things. Don't burden it. Questions to hear before we connect it back to rotational motion? So if I have an object that is rotating about some central point, this VI is the speed of some particular point on here. Well, one thing that all these points have in common is that they have the same angular speed. We have this object here that it's called a rigid object. In other words, as part of it moves, the whole thing moves with it. Doors are rigid objects. If a door were not a rigid object, that means if I pushed on the outside might bend, but the inside might just stay where it was. We're not dealing with that. We're just dealing with something that will rotate the whole thing through. So that everything in this object has the same angular speed. It all goes through the same angle in the same amount of time. 1/2 times the sum of the mass at some point in here times the radius or the distance to that point. So if this point right here is mass 1, this would be radius 1, because it's traveling through a circle of that radius, times omega squared. We are nearing the end. So it's 1/2. Oops, forgot my sum sign. 1/2 times the sum, MI/RI squared, omega squared, just squaring what's inside here. 2 more steps to go. Omega squared is constant. Everything that's rotating through the same speed, so I can just pull that out like I did with the 1/2. So I got a 1/2 omega squared times the sum of MI/RI squared. Doesn't that look so much simpler than what we started with? You might not think so, but it actually is. This right here, that's the moment of inertia. Or rotational inertia, depending upon the textbook.
I'm sorry, is that underneath the sum sign? Is that an I equals 1?
Yes, because I broke the door up into n pieces, and this is just the notation of I'm adding up. So if I break it up into 100 pieces, that means I'm going to add up all the ones from the first one to the 100th one.
Okay.
Any other questions at this point before I talk about why this is actually simpler? So if I have an object that is rotating, ultimately I have 1/2 mv squared at the heart of it, at the core, at the heart of it. But if I think about a piece rotating, the speeds vary depending upon where I am. And so if I take the rotation into account, I have a kinetic energy formula of 1/2 I omega squared. Or omega squared I. I typically is written first. And so if we have a ball here that is spinning, all you have to do is figure out what the moment of inertia of the ball is. Break it up into an infinite number of tiny little masses and figure out the distance to them and just do it that way. Which again, might not seem like it's easier, except for the fact that the hard work's already been done. And every beginning textbook will have a page like this as soon as I find it. Too far. There we go. Page 138 in your textbook. They have the formulas already done for certain objects. So now they don't actually have this one. This would be considered close to a thin-shelled sphere. because it's empty inside. All the mass is pretty much on the surface here. But if you went through this, broke it up into an infinite number of pieces, and calculated it, you would find that the moment of inertia for the ball is, make sure I have the correct one, all right, it's going to be 2/3 times the entire mass times the radius of the ball squared. This one's not in the chart. If we did a solid ball, so I've got a super ball here, it's solid all the way through. The moment of inertia of this one, they've already done it, this one is in the book, solid sphere rotating about the center. I is equal to 2/5 times the entire mass of this thing times the radius of it squared.
Which one was the 2/3 one? Was that the soft sphere?
The 2/3 is the hollow sphere.
Hollow.
In the math and physics textbook, they generally call it a thin-shelled sphere. If we take something like this and start rotating it, almost all of the mass is on the outside. The spokes provide very little mass. And so something like this, it's not on the table here, but you can approximate it. If you assume that the spokes are massless, then you treat this as a hoop spinning about its center, which is the second one. They call it hoop about normal axis. Now, hoop about diameter would be spinning it like this. That's hoop about diameter, and then that's hoop about normal axis. Normal meaning perpendicular. The axis is perpendicular to how this is rotating. If you want to treat the spokes as having mass, as having significance, well, you can treat them like thin rods. And in here, it's stick about end. So they have a formula for that. And so you would, since ultimately it's just a big sum, if you really wanted to find the true moment of inertia of this, you'd find moment of inertia of the outside using the hoop about normal axis, and then you would take each of the spokes, assuming you know the mass and the length, and then you'd probably estimate it as stick about end. And that's how you find moments of inertia. Right. Now, I know not everyone has the textbook, so I'm going to sort of read these out to you, and then I'm going to ask you a question about it. So they give simple pendulum, so that's just ball on the end of a string circling. Hoop about normal axis, which is what I just demonstrated. Hoop about diameter. Stick about end. Stick about center of gravity, so that would be, so stick about end is if it's rotating like that. Stick about center is it's rotating about the center. Or center of gravity. Solid cylinder and solid sphere. Those are the ones they give you. Suppose I asked you to find the moment of inertia of a disk. Which one would you use?
Cylinder?
What is the difference between a cylinder and a disk?
A cylinder is a cage shape. Yeah.
Okay. From a math point of view, what do the math people say is the difference? I think that's more of that in everyday world.
More of a height.
In terms of math and physics, there is no difference. A cylinder and a disk are the same thing. In terms of everyday life, I think it basically comes down to how thick it is, whether at what point it becomes a cylinder. There's probably a gray area in there. So if you ever, and I can't remember if Hewitt actually talks about disks in here, but if he does talk about a disk, he's talking about the cylinder. It's just, generally we think of disk as being flatter, but the thickness of the cylinder does not come into play. And so on, oh, I guess we have lab. I've posted that one. So I guess we'll meet Monday of next week. Or Wednesday, as people say today, these days. Wednesday of next week is our next class. And I will connect it. So I need to connect it to the stuff going down the ramp. Why does the distribution of mass matter? As Taylor said, one got down faster because it was not hollowed out, I believe was the wording we used. So we'll connect it to that. And then go on to explore other strange and wonderful things.